Okay, so in this very last lecture of this course, we are going to prove the theorem about the Frobenius kernel, which says the following. Well, so we recollect what everything we need. Let G be a finite group, a finite Frobenius group. So that, and H, a Frobenius complement. So this means that H is a subroot of G. It's different from 1, and the intersection of H with any of its conjugate is trivial if X does not belong to H. Of course, when X belongs to H, H to the X is just H, but if it's not, the intersection is trivial. Consider the subset, which is, as we discussed yesterday, a normal subset, which means it's closed under conjugation, N, which is given by the following. You take G, you subtract from G the union of all conjugates of H, okay, where H ranges in G, and you add, and then you add back 1, because I mean, we want this to be a subgroup, so there has to be 1 in it. And the claim is that N is a normal subgroup of G called the Frobenius kernel of G. And we saw in examples like S3 and A4 that indeed there is a normal subgroup like this. But so far, this is just a subset. So the idea is to show that, okay, that's the statement. Idea, extending the irreducible characters of the irreducible character phi, say, of H to irreducible characters phi star of G. Okay, extending means that phi star of H equals phi of H for H in H. Okay, and then we will see how to use this. I mean, to do this, we cannot use directly induced characters, because when you take an induced character, say if you induce from phi to, say, phi star, you obtain a character which has different degree, because the degree is multiplied by the index of H in G. And of course, you don't have this, yes, you don't have this here, okay? Because here the character, the degree of phi star and phi is the same, because it's the value of phi star or phi on 1. So let's see how the one proceeds. We'll do it in steps. So step 1. Each step is relatively elementary, but taken together, they represent quite a formidable proof. So let theta be a class function on H. Okay, so a class function meaning a function from, let's say, from H to C, which is invariant over conjugacy classes. We will exploit this in a second, such that theta of 1 is 0. So definitely this is not a character, because of course the value in 1 of a character is its degree, and is the size, say, of the matrices of which you are representing the group. But in step 4, no, step 3, we will be taking for theta a difference of characters, and then they may well have theta 1 equals 0. Then the claim the claim we are going to prove in this step, is that if you take the induced character, which will be recalled in a second, and then you restrict, so this is induced character, and then this is the restriction to H, the usual restriction map, then this is just theta, okay? In other words, if you consider the values of the induced characters over H, it's the same values as theta. So this is a good chance to remind what the induced character is. So the induced character is the following. We want to know what the value is on H, so we compute the induced character over an element H, which is generic for the moment, but then it will be an element of H. So this is 1 over, well, this is for normalization purposes. We have to, okay, 1 over the order of H, and then you sum over all x in G, theta naught x H x inverse, where recall that theta naught is not a character, but it's still a class function. Theta naught, we'll recall it here. Theta naught of G is theta of G if G is in H, and is 0 if G is not in H. Okay, so you first extend the theta to a function on G given by this, I mean, simply 0 outside H, and then you take this sum over all conjugates. But the only chance for theta 0 of something to be different from 0 is when that particular something is in H. So when this is in H, okay, then this means that this element lies in H, and in H x inverse, okay? And this can only happen if x is in H, okay? So what we obtain is that theta G of H is 1 over the order of H, sum over x in H of theta x H x inverse, okay, and this since theta is a class function on H, and we are conjugating over H, this will be simply the sum over x in H of theta of H. So this is 1 over order of H times theta of H, which is just theta of H, because this is the sum order of H times of the same element, okay? So, yes. Oh, yes, and of course, yes, what I was getting wrong before, either x in H or x is not in H, and H is 1, and now we use the fact that theta 1 is 0, okay? Okay, because all these elements become 0 if H is 1, okay? Because the intersection of this is 1. So either x is in H and we get this, or if x is not in H, then this element has to be 1, so H is 1, and we know that the value is 0. Okay, so we have obtained this fact, sorry for the slight mishap, that if you induce theta to G and then consider its value on H, you get theta, okay? So the value let's say for H in H, okay? So when H is in H, you consider this, because that's just what we want to know, that the restriction to H, and we get this. Okay, so that's the first important step that we are going to use. Let's say, no, sorry. Let's consider now step 2. Step 2, well, it's what I already anticipated, the fact that if you consider this on 1, this is theta of 1 and is 0, okay? This is something I have already discussed here. Well, of course, there's a stupid misprint here. This is theta of 1, Okay, but I put the 0 inside, but of course it's theta of 1, which is 0. But there's no 0 in the group. Okay, so I corrected this. Okay, good. Okay, so the value on 1 is 0. Now let's come to step 3. We want to apply this. So we need a class function on H which has value 0 on 1. And what we do is the following. We consider an irreducible character of H, which we want to extend to G, which is different from the trivial character, okay? And we consider what? Theta, which is the difference between phi and a multiple phi of 1 of H, of the trivial character. So this is an irreducible character different from 1, and this is the trivial character, the character that has always value 1, okay? And this is a difference of character. I mean, this is a character because it's the sum of the trivial representation takes phi 1 times. So this is a difference of character, okay? In particular, of course, we will have that this is, as a difference of character, this is a class function, because characters are class function. And of course, what's theta of 1? This is phi of 1 minus phi of 1. This character has value 1 over all, on all elements. So this times 1, and this is 0, okay? So we are in a position to use step 1. So we go into step 1. In step 4, what we do, we consider theta the induced character. Okay, this is induced character. And we consider the inner product of theta g with itself. Okay, by Frobenius reciprocity, so to apply this, it tells you that if you have an induced class function, not necessarily a character, and here another character, this is the same as the same inner product over H, where here you consider theta, the one you started with. So here you have theta to the G, you have theta. And here you have restriction of this to H. Okay, so here's the duality, that in this direction on the first component you go from theta to the induced character, and in the opposite direction from this you go from this class function to the restriction. But since this is a sum over the element of H, we have just proved that this is nothing else but theta. Okay, okay, this is step 1. Okay, and so theta is and of course there's another mistake. This is just okay. Let me rewrite this. This phi minus phi 1. No, this is correct. Very sorry. I was looking at the wrong. I mean, theta is phi minus phi 1 times the trivial character. So when you consider this scalar product, okay, the inner product, so what do we get? We get, let's write it, phi minus phi 1, 1h, phi minus phi 1 of h. And now note that phi is different from, is an irreducible character and is different from the trivial character, which is also an irreducible character. So the orthogonality relation, you see, we are exploiting more or less everything we did in this course, tells you that the inner product of phi with 1h is trivial, okay? Because, so we'll write it here, 1h phi is 0, orthogonality relations, okay? Write it here. And on the other hand, if you consider, since phi is irreducible, this inner product, scalar product is 1, and the same holds trivially for this. So when you distribute here, what you will obtain, you'll obtain, well, let's write it this, okay? And then 1h is 1, except that we have a minus phi in front. So this will be plus phi 1 squared, say 1h. Okay, so what we obtain, this is 1 plus phi 1 squared, okay? We have just used the orthogonality relations on H, okay? So what we have obtained that the inner product of theta g with itself is 1 plus phi 1 squared. Okay. Now, okay, let's get to step 5. Okay, so theta g is the induced class function of a certain class function. This class function on H. Okay, so theta g is a class function on G, and as such, it's a linear combination with, well, we'll explain why, with integer coefficients of irreducible characters. The reason is that we proved that irreducible characters are a basis of the space of class functions. Recall why this holds, because there are as many irreducible characters as conjugacy classes, and then the space of class functions, so class function from G to C, has exactly the dimension equal to the number of conjugacy classes, because these are functions that are constants of conjugacy classes. And since, as we just recalled, the irreducible characters are orthonormal, they are a basis of this space, okay? So this is a class function. Actually, this will be repeated afterwards. You see, theta is a difference of characters, okay? So since we have proved 2 weeks ago that if you take a character and induce it up to G, a character of H, and induce it up to G, you will obtain again a character of G. Since theta is a difference of characters, also theta G will be a difference of characters, okay? I'll explain this in a second. This is theta is a class function of G. Moreover, theta is a difference of characters of H. So theta G is a difference of characters of G, okay? Because if you take a character of H and induce it up to G, you'll obtain a character. If you have a difference of character, you'll obtain a difference of character, okay? So this means that theta G thus is a linear combination of irreducible characters of G with integer coefficients. Because these coefficients will be, I mean, it's a difference of character. So if you take a character, the coefficients will be non-negative integers. If you take a difference of characters, they will possibly become negative integers. So in general, integer coefficient. And we are wondering what this coefficient is, okay? So this coefficient of 1G when writing theta G as a linear combination of characters or irreducible characters. Again, why is it this? Because of the orthogonal relations. Okay, this is just a projection on 1G. So Once more, we use Frobenius reciprocity. And let's recall how it works. This compares an inner product over G to an inner product over H. The idea is when you go right to left, you go from theta to theta G. When you go left to right, you take this and you consider the restriction. And the restriction is just, this is the trivial character. The character has value 1 or one element of G. And of course, it restricts to the trivial character of H, simply because the trivial character of G restricted to H is nothing else than the trivial character of H. Okay, and what's this? Well, you simply check what theta is. You see theta is the difference of an irreducible character minus phi I times 1h. So if you take the inner product of theta with 1h, phi is different from 1h, so this inner product is 0. You get minus phi 1, okay? And the explanation are repeated here because theta is nothing else but phi different from 1h minus phi 1 times 1h. So when you take this inner product, this selects these coefficients of 1h here, okay? And so, well, okay, but we want to continue. And so this is important. So 1g appears minus phi 1 times in the decomposition when writing theta to the g as a linear combination of a reducible character. So this means that theta g will be minus phi 1, 1g, okay, this coefficient we found here, plus phi star, okay, which is another class function on G, actually a difference of characters. What's important is that it does not contain 1G anymore, because the number of times 1G appears in theta G is exactly minus phi 1. Since I already taken care of this, 1G does not appear anymore in what's left. Okay, there will be other irreducible characters. And the point is, I want to prove that this is actually an irreducible character. And it's this extension I was aiming at. So let's see how this works out. Step 6. Okay, so let's recall what I just wrote is that theta G is, let me repeat this, is minus phi 1 times 1G plus phi star. So this is not a character, there's a minus in front, it's the difference of character. Plus phi star, where what's important is that 1G does not appear in phi star. So when we consider the inner product of theta G with theta G, okay, again, 1G and phi star are orthogonal. So we'll obtain a phi 1 square here, okay, orthogonality relation 1G, 1G, the inner product is 1, plus phi star, okay? But recall that from step 4, okay, so this is step 5, okay, this. But step 4 told us that, let me check whether I wrote it correctly. Yes, that this inner product equals 1 plus phi 1 square, okay? And so this is 1 plus phi 1 square. You see, of course, these two cancel out. So what we obtain that, also this is over G, phi star G equal 1. Now there's a slightly tricky point because you see step 7. So remember, all these elements we are taking, theta G and so on, so theta g and thus phi star are difference of characters. Okay, and so but by the remark I made here, so a character is a linear combination, as I said, with non-negative non-negative integer coefficients of irreducible characters. So when you take a difference of characters, the coefficients are integers, possibly negative. So this means that phi star is equal to a sum over the irreducible characters of G. Well, one does not appear, but this is not important, of a certain coefficient chi, where the a chi are integers, okay? So when you consider this product, by the usual orthogonality relations, okay, these are integers, okay? So, okay, by the orthogonality relations, you will get the sum over the reducible characters of a chi squared. It would actually be a chi conjugate a chi, okay, because the inner product is linear in the second character and sesquilinear in the first one, in the second component, and sesquilinear in the first one. That is, you get the conjugate out of this. But of course, these are integers, so so this implies that this is just a k squared. And okay, what can a sum of squares of integer be if the result is 1? This means that they are all 0 except 1, which is plus or minus 1. So what we obtain that only one coefficient is different from 0, and has to be plus or minus 1. We obtain that phi star, that plus or minus phi star is irreducible. Okay? Or if you prefer, that phi star is plus or minus an irreducible, which is the same. Okay? You just bring the sign to the other side. So we want to prove actually that it's an irreducible, not minus an irreducible. How do you prove this? Well, that's easy. So step 8, which is in red, but just by mistake. So let's rewrite it in case it looks like something fun is going on. Step 8. Step 8 claim. So okay, we know already that plus or minus phi star is an irreducible character. Claim phi star is actually an irreducible character. And this will be the extension we are looking for, okay? But we prove more, because more. Phi star is an extension of phi, okay? Which means we compute phi star of h for h in h, and we want to see what we get. So phi star, we should recall where phi star comes out. Phi star is here, okay, you see? So yes. So phi star is theta to the g plus, you take this to the other side, phi 1 times 1g, okay? So this is theta g, not in red. Minus plus phi of 1, because, okay, I'll write it here, I remind you here that phi star is theta g plus phi 1 of g, okay? So 1g is always values 1 or anything, so you get this. And remember, step 1 tells you that the value of theta g on h, on an element of h, is theta of h. Okay? And this is exactly phi of h, because once more, let's get back. This was in step, yes, in step 3, you see phi is theta plus phi 1 of 1h, okay? So we have proved that phi star is an extension of phi, that the value of phi star on H are the same as the value of phi. And moreover, of course, this tells you that phi star of 1 is phi 1. And this is the degree. Recall that phi is an irreducible character of H. So this is definitely greater than 0. So we were in doubt whether phi star is a character or the opposite of a character. But if it's the opposite of a character, then the value is 1 is negative, okay? So this implies that, that phi star is an irreducible character of G. Just to explain, I have written it like this. So I know that phi star is equal plus or minus chi for chi irreducible for some chi, an irreducible character of G, okay? So phi star of 1 is equal plus or minus chi 1. So it's positive if the sign is plus, or it's negative if the sign is minus. But phi star of 1 is positive, so the sign has to be the plus, okay? Because this value is positive. And now we are nearly there, although we will have to consider an important thing. So step 9. So for every irreducible character of H different from 1H, we have obtained an extension phi star of G. Well, note that if this is for character different from the trivial character, but of course the trivial character of H extends to the trivial character of G. So no particular problems here, okay? An extension phi star, which is irreducible in H. So remember, what does an extension means? It means that phi star of H equals phi of H if H is in H, okay? And now what we do, consider M, which is the intersection over all phi in the irreducible character of H of the kernel of phi star. Of course, this is a kernel of a character. We remind you in a second what this is. So this is definitely a normal subgroup of G. And my claim is that this is exactly N, okay? So remember, N is the normal subset which I want to prove is a subgroup. We'll recall this in a second. So step 10, okay, so I'll copy it to the next page. Okay. So step 10 says that my claim is that M intersect H trivially. Okay. Note that once I know this, this will imply what? I mean, conjugate. So this is trivial. If you conjugate this with an H, of course, you obtain this for X in G. But remember that M is a normal subgroup because it's an intersection of normal subgroups of kernels. And so this is just M intersect HX. So once we know that M intersects H trivially, it intersects every conjugate of H trivially. How do we prove this? Well, okay. So let's say G, no, let's call it H, it's simpler. Suppose that H is in M intersect H, okay? So for all irreducible character of H, different from 1H, this is 1H, we have that phi star, okay, of H is phi star of 1. Okay, so this is, because that's what the kernel of a character is, okay? So the kernel of a character is all elements, we'll call it, let's call it T, because I don't want to specify the group, such that chi of T is equal to chi of 1 to the degree. And recall that this is just, it was a little proof involving a lemma on roots of unity. This is just the kernel of the associated representation, okay? So let's recall this equal the kernel of rho if, say, chi of T is the trace of rho of T. So if rho is a representation that affords chi, okay? We prove this. It's a good way to look back at this. There's a little lemma on roots of unity that prove this. So you have this element of H, which is in the kernel of all these phi star. So which means that phi star of H is phi star of 1. But remember that phi star is an extension of phi, and H is in H. So this is just phi of 1, okay? And sorry, phi of H. And similarly, this is phi of 1, again, because both H and 1 are in H, okay? So you see, we started with something, with an element which is in H and in the kernel of phi star, okay? But, okay, let's write it here. So H is in the kernel of phi star, that is, and so on. But we ended up with H being in the kernel of phi, okay? For all phi in the reducible character of H. Note that this is actually true for phi different from 1H, but note that so 1H is the character which is 1 on all elements. So the kernel of 1H is the whole of H. So, I mean, so any H is in the kernel of 1. Even the fact that we have phi different from, so the fact that phi is different from the trivial character does not count, because every element is in any case in the kernel of the trivial character. So this is in the kernel of this, and I claim that this let's put a question mark, I claim that this implies that H is 1, which is exactly what I wanted to prove. Why this claim? So let's see this. It's an argument that so this is an aside, and the aside tells you, I'll do it for H, but which is after all an arbitrary group, say for an arbitrary group H. Okay, so let H be an arbitrary finite group. I don't think I've ever done this, but I mean, it's very close to something we have done. And then the intersection of the kernels of all irreducible characters of H is trivial. Why is it so? Well, recall that there is an algebra isomorphism between the group algebra, this has played an important role in many things, and the direct sum over chi, the irreducible characters of H. Okay, so I have chosen H, this is H. And here you have the endomorphism, that is the matrix ring of V chi, where this is a module which affords this character, okay? So the group algebra is isomorphic to the sum of matrix rings. So these endomorphisms, which are, say, endomorphisms over C, these are matrix algebras, we call, yeah. And how does this work? Well, if you take an element here, which I call sigma, okay, this goes to what? It goes to something that on the component chi, send the vector V here to V sigma, okay, when this is the module action of CH on V chi, okay, the module action. Good. So here we have an element. So let's say let H be in that intersection of kernels, okay, overall irreducible character. So this means that this H goes to what? V goes to V, because if it's going to the kernel, it has to go to the identity, okay? Because being in the kernel means that on every module V chi is actually acts as the identity. But then, of course, the same holds for 1, okay? Because if you take the element 1, this sends V to V times 1, which is V, okay? So this is an algebra isomorphism. So if you consider H minus 1, okay, this goes to what? Well, V, it goes to, V goes to V minus V, okay? Because you first act on V with H, which does nothing, and then you act with 1, which does nothing. So this is 0, okay? So what does this mean? This means that this, okay, is that clear? Let me rewrite it because I want this to be clear. So H minus 1 goes to the map that sends V to V H minus 1 on each component chi, okay? But this is, V is sent then to VH minus V times 1. But V times H, okay, I can rewrite it this. H acts trivially, and so does 1. So this is 0, okay? So what have we obtained? We have obtained that this H minus 1 is in the kernel of this isomorphism, which I'll call F, okay? I ran out of space. Well, let's write it this way. So H minus 1 is in the kernel of F. And remember, this is an isomorphism, so this is 0, okay? So what we obtained, sorry, I'll continue here. So H minus 1 is 0, so H is 1. So remember, we have proved that this is an isomorphism. So H minus 1 is in the kernel of it, the kernel is 0, so H is 1, okay? So this is an important fact. Let's close the parenthesis here, that, that the intersection of the kernels of all irreducible characters of an arbitrary finite group is trivial, okay? And, okay, fine, yes. And yes, and that's the reason why H is 1 here, okay? Why M intersect H is 1 here, because an element in intersection has the property to be in the kernel of all irreducible characters of H, okay? And we have just proved that this happens only for 1. And now we are close to the end, because my claim, sorry, the final claim, we claim that M is equals to N. So let's recall what these two things are. This is the intersection of the kernels of phi star, okay? If phi ranges over the irreducible characters of H different from the trivial one. And this is what you obtain from G if you subtract the conjugates and then add back 1 to have a subgroup. So we want to prove that these two are equal. We know that this is a normal subgroup of G, and this will prove the claim, okay? So how do you do that? Good. First, so we have to prove that M is contained in N and converse. So let's prove that M is contained in N, this part. But this is what happens. Okay, for a moment, let's stop the writing. M is contained in N, but that's rather clear because we have just proved here that M intersect trivially all conjugates of H, okay? So, clear? as M intersect trivially all conjugates of H. So M is contained in G, but intersect trivially all of this, so it contained in G minus this intersection. Of course, 1 is always there. As to the converse, well, 1, of course, is contained in M. So suppose you have an element of N different from 1, because, of course, 1 is in both things. And then, yes, and then we compute phi star of G minus phi star of 1. And of course, what I want to prove is this is 0, okay? I'll repeat this in a second. Because if it's 0, this means that G is in the kernel of phi star, okay, for an arbitrary, for phi irreducible character of H, say different from 1, though this is not particularly important. We want to prove that this is 0. So what's this? Okay, so we already said that phi star is an extension of phi, so on 1, which is an element of H, this is trivial, okay? But let's look at this. This is actually what? This is the phi star minus phi 1 of 1G computed on G. Okay, because if you take this thing and you compute on G, you get phi star of G, and then this is the trivial character, so on G is 1. But if you look back, this is exactly, okay, let's look back at this. This is exactly, should be somewhere, okay, fine. Phi star is exactly, just a second. Yes, so you see, theta G is just phi star minus phi 1 of 1G, okay? So theta G is phi star minus this. So if you go back here, this difference is exactly theta of G computed on G, okay? But this is important. This is an induced character, okay? And let's recall the formula here. Well, recall theta naught, theta 0 is 0 outside H, okay? So this can only be different from 0 if this element, if H lies in a conjugate of H, okay? If this element lies in a conjugate of H. So since G is in N, G does not lie in any conjugate of H. So this is 0. Why? Well, let's go to the next page. Because G is not in any conjugate of H. Let's recall this point because it's critical. So perhaps I should rewrite this. This is a G, sorry. Let's write it in red because it's a correction. So let's rewrite this. So this is 1 over H, sum x in G, theta naught, x G x inverse. Okay, so this can be non-zero. Okay, only if one of these is non-zero, if and only if there is an H in G, x in G, such that xg x inverse is in H, okay, because theta naught is 0 outside H. And of course, this means that G is in the conjugate H of X, H via X, okay? But the point is that we have taken an element of N, which is not in, which is different from 1, which is not in any conjugate. N is what you obtain from G if you take away all conjugates. And so this means that this is 0. okay? Y, I'll write it here as G, is not in any conjugate of H. And this ends the proof, okay? Because we have proved that this N, this subset, is actually a subgroup, a normal subgroup of G, okay? Okay, that's it. I finished slightly early, but this was a dense proof. And that's also the end of the course. Thanks for listening.